In this exam question, we are asked to draw the conjugate acid for each base, and then place the following bases in order of increasing basicity, weakest base being first, and we're going to explain our choices for putting them in order. First conjugate acid has the extra proton on the nitrogen. Nitrogen develops a plus charge. Second one, similarly, nitrogen develops a plus charge. Pyridine, different category, becomes a pyridinium. This is another pyridinium with a electronegative fluorine on there. Here's a third pyridinium with a methyl. Why did I choose to put the H on the imidazole on this nitrogen? The reason is this nitrogen has a lone pair which is being used for aromaticity. You will lose aromaticity if you put a proton there. Similarly for this imidazole. The last two molecules are aniline derivatives. This is a methoxyaniline, and the last one is just an anilinium. The broad categories of acids and bases will be highlighted shortly. 1 and 2 are in the category of aliphatic amines. Nitrogen is attached to sp3 carbons. Nitrogen is also sp3. This next category, pyridine derivatives. Third category, imidazole derivatives. And the fourth category, aniline derivatives. Aliphatic amines, because N is sp3, it is the best cation. 25% S doesn't bring the plus as close to the nucleus. So these are our two best amines. Secondary, which is 2, has the best combination of hyperconjugation and hydrogen bonding when N is plus. This makes 2 the best base, 1 a close second. Aliphatic amines are the best bases. The worst bases of the categories here are the aniline derivatives. The reason is nitrogen lone pair can no longer resonate with benzene after it is protonated. So now we're choosing between 8 and 9 for worst and second worst. The OCH3 has a lone pair in 8. Can resonate to stabilize N+. Which makes 8 the better base and 9 the worst base. Eight's the better base, 9's the worst base. Pyridine derivatives are the second worst category of bases. The reason there is that the nitrogen itself is sp2 hybridized. sp2 hybridized N plus brings plus closer to the nucleus than sp3. Because it is 33% S. So now we have to choose between 3, 4, and 5. Which cation is best stabilized? In 3, 4, 5, which of these cations is best stabilized? Well, a methyl is going to best stabilize the cation by way of hyperconjugation. So in 5, methyl stabilizes N plus by hyperconjugation. That puts 5 as the best of these 3. The fluorine in 4 destabilizes N plus. By inductive effect. Sometimes an inductive effect is a negative effect. When you're pulling electrons away from a cation like fluorine does, that destabilizes the cation. So that puts fluorine as the worst in this trio. And nothing on the pyridine at all as the middle. And then second best bases are the imidazoles. Our only question now is which imidazole is more stable in its cation form, because that will be the one that arose from the more strong base. And just like fluorine destabilizes N+, nitro does it even more so. So we do not like the nitro, which is 6. We got our second best bases. And nitro destabilizes N+ by inductive effect. So the nitro one is the worst base. Nitro being on 6. And 7 not having the nitro. So, brief explanation of best to worst again. We have the two aliphatic amines, secondary being better than tertiary because it has the best combination of, when you're comparing 1 and 2, the 2 has the best combination of hyperconjugation and hydrogen bonding when N is plus, and that's when it is a secondary. Second best bases, imidazoles. We didn't explain why they're second best. They have two equally stable resonance forms. That's why they're second best. This is our explanation of why the aniline derivatives are the worst bases. The nitrogen lone pair can no longer resonate with benzene after it is protonated. Second worst, why are pyridine the second worst bases? sp2 hybridization on N plus brings plus closer to the nucleus than sp3. The same argument holds for imidazole, sp2 hybridized, but the imidazole has two equally stable resonance forms, whereas a pyridine does not. There's nothing, no other nitrogen here to help resonate to an equally stable resonance form. So I believe we have a adequate explanation here, and these are now in the right order, which brings to a close this part of the acid-base problems.